Hi, this is a video covering graphing inequalities and then also linear programming, which is just a fancy word for applications that involve linear inequalities. And so for our first example, we'll look at something really basic just to kind of remind you. This is a concept that you probably learned back in your algebra classes. We want to graph this, the equation 2x minus 5y is less than 10. And so what we'll do is, to get started, we'll think about what the line would look like that corresponds to this. So we'll graph 2x minus 5y equals 10. And then we'll analyze what that inequality does to the overall graph after we get the line started. Now, one thing that you might remember is that if we have a strict inequality, such as this or this, then we're going to have a dashed line because where the line falls is not included in the equation. And if we have an inequality that includes equals, then we'll have a solid line. We'll have a couple examples of each of these in this video. I think the easiest way to graph a line in this format is to think about the x and y coordinates. So in this particular case, if x were equal to 0, then y would be equal to -2. And if y is equal to 0, then x is going to be equal to 5. So I'll use those ideas for my graph. I think I'm going to maybe try to skip every other line just to make this easier to graph. So -2 is down here. And 5 is going to be up here. And so my line is going to be going between these 2 points, and I'm going to make it dashed, right? Because I don't have equality on the line. And then what this is asking us is to show all the places where this equation is true, and it's going to be a set of points that will make this true. One of the ways to determine where we're going to shade is to plug in the origin. So I'm going to plug in the origin. Let's test the point 0, 0 in the original. 2 times 0 minus 5 times 0 is less than 10. Yeah, 0 is less than 10. That's true. So because that point made this inequality true, that means that the origin is included in the solution set. So I'm going to be shading everything above the line that's including the origin. This means that any point that I choose in this particular area should make the equation true. Let's try a different one. Let's take the point, say, 2, 2. Let's test 2, 2. 2 times 2 minus 5 times 2, is that less than 10? 4 minus 10, which is -6. Yeah, that's less than 10. So that makes the inequality true. For our next example, we'll look at one that's maybe set up a little bit more in a more complicated way. Let's look at 2x minus 6y greater than or equal to 8 plus 2y. Now, we can follow the same idea that we did in the last problem. We just need to sort of rearrange this before we get started. So I will subtract 2y from both sides and rewrite this as 2x minus 8y greater than or equal to 8. And so I'm going to think about graphing the line 2x minus 8y equals 8. And the y coordinate for this is going to be 0, 4. And the x coordinate of this is going to be the y coordinate is going to be 0, -1. Just confused myself there. -1. And the x coordinate is going to be 4, 0. So let's put this together on a graph. So let's see, 1, 2, 3, 4. So that's 1 and here. So it looks like my line is going to be here. I'm making this a solid line this time because I have equality in the inequality symbol. And then I'm going to test the origin 0, 0 to see which side to shade. So 2 times 0 minus 6 times 0. Is that greater than or equal to 8 plus 2 times 0? So I've got 0 greater than or equal to 8. This is false, right? So because this is false, we're going to shade on the side that the origin is not included. And all of those points, anything in that shaded region will make that inequality true. The next set of examples are going to take a couple different inequalities and have us graph them simultaneously. And that leads us to linear programming, because often when you have a problem that you're trying to solve in business, there are multiple constraints that you're dealing with at the same time. So for this next example, let's graph x minus y greater than or equal to -2, x plus y less than or equal to 6, x greater than or equal to 0, and y greater than or equal to 0. All right. So the first thing I'll do is I will graph x minus y equals -2. The x and y intercepts for this, let's move down, x minus y equals -2. I'm going to have 0, 2, and then -2, 0, right? So that first line is going to be here. Like that. All right. And then our second line, I'll make it a different color. It's going to be x plus y equals 6. So we'll have 0, 6, and 6, 0. So that line is going to be, let's see, 1, 2, 3, 4, 5. I need to make this up more. One, 2, 3, 4, 5, 6. 6. There we go. So this is going to be like this. And then the last two lines are actually just the x and the y-axis, right? X, we're wanting x to be greater than 0, and we're wanting y to also be greater than 0. So that means that we're going to be graphing something in the first quadrant there. So if I look at sort of the region that's created by all of these lines, and taking also into account being on this side of the y-axis and on this side of the x-axis, I'm going to have this area in here as my solution. In this case, we had greater than or equal or less than or equal in all cases, and so all of the lines are going to be solid in that way. All right, let's do one more example like that. Let's graph y less than or equal to 2x plus 1, y greater than or equal to negative 2x plus 1, and x minus 2 less than or equal to 0. So looking at these lines, y equals 2x plus 1, I have the points 0, 1, and when y is equal to 0, x is equal to negative 1/2. For the second line, y equals, is that right? Pause for a second, just double check. Okay, I'm back. For a second equation, we have, I'll do that one in green. Y equals negative 2x plus 1. So we have the points 0, 1 also. Oops. And, oh, yeah, see, I knew that I had done that incorrectly. When x is 0, y is 1. When y is 0, this should be a negative 1/2. Goodness, I knew that was wrong when I wrote it. Negative 1/2, comma 0. There we go. And then this one will be 1/2, comma 0. Right? Yeah. Okay. And then for the last one, this is the same as the line. Let's get a different color here. Let's use blue. This is the line x equals 2. I'll have to move the 2 over to the other side. All right, let's put these components together. Axis black. I don't know why it's doing that. Okay. So for the first line, we're at 0, 1, which is here, and then negative 1/2, 0, which is here. So this line is going to be like that. And then for our second line, we're at 0, 1, and then 1/2, 0, so here. And then our last line is x equals 2, which is over here. Like that. Oops, that was weird. Undo that. Right, there's my third line. And we're probably thinking it's going to be that triangle there on the inside, but what I'll do just to make sure is I'll pick a point somewhere in there. Let's pick the point 1, 1. And I'm just going to test it in these areas to make sure that they're true. Let's test the point. 1, 1. So for the first equation, we would have 1 less than or equal to 2 times 1 plus 1. That says, this is equation 1. 1 less than or equal to 3. Yeah, that's true. For the second equation, we have 1 greater than or equal to negative 2 times 1 plus 1. So 1 is greater than or equal to negative 1. Yeah, that's true. And then the last one, we have 1 minus 2 less than or equal to 0. That's weird. I made a little square. And negative 1 is less than or equal to 0. So that's true. So we're going to be shading in this whole region here. All right, for our next couple examples, we'll do some application problems. These are called linear programming, just fancy words for word problems that involve inequalities. So we have a mill that's converting logs into lumber and plywood. In a given week, the mill can turn out 400 units of production, of which at least 100 units will be lumber and 150 units will be plywood. The profit for each is $25 per unit for the lumber and $38 per unit for the plywood. We want to know how many units they should produce to maximize their profits and then find what that maximum profit is. So let's start by setting up variables. So let's let X be the number of units of lumber and then we'll let Y be the number of units of plywood. For those of you that don't know, lumber is going to be long, skinny boards, whereas plywood is going to be a big, flat piece of wood. So that's the difference between them. And then because we're trying to find profit, we're going to have P is going to be profit. And so the amount of money that we're going to be making is going to be $25 for every unit of lumber that we sell. So that's 25x. And then $38 for every unit of plywood. So that's going to be Y. So that's our profit equation. And then the constraints that we have are that the maximum units in total production is 400. So X plus Y is going to be less than or equal to 400. That's 400 is the max we can produce. And then to meet the customer demand, we have to have at least 100 units of lumber. So X has to be greater than or equal to 100. And then we need to have at least 150 units of plywood. So Y has to be greater than or equal to 150. So then what we're going to do is graph this system. And I'm going to scale the axis because I've got values that are in the hundreds in this case. So let's go by hundreds. So this will be, I need to go up to 400. So let's do 100, 200, 300, 400. Right, so this is 400, 100. All right, so for our first equation, we're going to have X plus Y equals 400. I'm looking at X plus Y equals 400. So the two intercepts are going to be 400, right? So we'll graph that line here. The second line is going to be x equals 100. Which is going to be, goodness, OneNote's freaking out today. There we go. Which is going to be here. And then the other line is going to be y equals 150. So that's going to be here. I don't like where that is. It should be right on the line. Right here. I don't know what's happening with my pen today. Maybe the battery's dying. So what we need to analyze are the three intersection points, right? This is one here, this is one here, and this is one here. We can kind of see by looking at the graph what they are, but if we aren't sure, what we're doing is we're actually solving this set of equations right here. And so we're looking at those intersection points. So one of the points is going to be this is 150. It looks like it's 150. No, that's 100, 200. This is 250, 150. Up here, our x value is 100, and then our y value and then the y value is 300. And then for our last point, we're at 100, 150, right? 100, 150. It's this point here. So now what we do is we plug in each of those vertices to see which one gives us the maximum profit, because anytime that you have multiple constraints, the maximum or minimum point will fall at one of the intersection points. So now we're going to take the profit function that we had, 25x plus 38y, and we're going to plug in the 3 points. We had 100, 150 was one of them. We had 100, 300 was another one. And we had 250, 150. And we're plugging them into this equation. So we're going to analyze 25 times 100 plus 38 times 150. 25 times 100 plus 38 times 300. My pen is freaking out today. 25 times 250 plus 38 times 150. And we would get, this one's 8,200. This one's 13,900. And this one's 11,950. So it looks like this is going to be the combination that gives us our maximum. So the maximum profit is $13,900 when 100 units of lumber and 300 units of plywood are produced. Okay, I have one more application problem like that. This one is instead looking at minimizing a system. This is a school board that is hiring teachers and teachers' aides, and they want to minimize their costs. The average salary for a teacher is $53,000, and the average salary for the teacher's aide is $23,600. They have some constraints here about the number of people that can be in the building. They can't have more than 50, and at least, but they have to have a minimum of 20. They have to have 12 aides, and the number of teachers must be twice the number of aides. So we're going to try to figure out the combination of teachers and teachers' aides to hire that will minimize the salary. You can understand part of the reason for the constraints in this case is that obviously the least expensive thing to do would be to hire all teachers' aides because they get paid less. But obviously we would need to have some master teachers who are credentialed to be in the classroom. All right, so let's set up our variables to start. Let's let X be the number of teachers, and we'll have Y be the number of teachers' aides. Okay. The total cost is going to be 53,000 times the number of teachers, and then 23,600 times the number of teachers' aides. Now, we said that there can't be more than 50 faculty, so X plus Y has to be less than or equal to 50. And there also has to be a minimum of 20 people, probably based on the number of children at that school. And then we also need to have at least 12 aides, also probably based on the demand for certain needs of students. And then the number of teachers has to be twice the number of teachers' aides. So those are all of our constraints. And then we will put this together in a graph. And I'm going to make this graph just be the first quadrant because I think it's safe to say that the answers in all of these cases are going to be positive, right? We're not going to have a negative number of teachers or a negative number of teachers' aides. So our first equation will be X plus Y equals 50. Let me count this off by, let's see, would 10s work? Yeah, probably. Let's go 10, 20, 30. Oops. Okay. 10, 20, 30, 40, 50. 10. Make this, I actually think I want to space this out more. I'm making these graphs so small, I'm making it hard on myself. All right. Make 10, 20, 30, 40, 50, 10. I'm going to regret going by threes. 20, 30, 40, 50. Okay, so that first line is going to be like this. Pretend that's straight. Then our second line is X plus Y equals 20. So that line is actually going to be here. These two lines are parallel. And then we also have Y equals 12. And instead of writing this as x equals 2y, I'm going to write this as 1/2 x equals y. Y equals 12 is going to be, let's see, this is 10, so it's going to be around here-ish. And then 1/2 y, I'm going to go to the origin and I'm going to go up by a half. So I'll go up, let's see, like this. That's my second line there. And so where is my solution? I've got a lot of different things going on here, right? So what you normally do is you try to find something to sort of grab onto. Let's look at this last equation. We want x to be greater than 2y. So I think that we're going to be below this line. I think we're going to be below this line in that way. Let's test a point. If I were to test the point down here, I'm looking at this equation here, x greater than or equal to 2y. If I were to test, let's say something down here, 1, -1, to show that we're shading below that line. We'd have 1 greater than or equal to 2 times -1. Yeah, that works. So that's how I'm kind of analyzing that. I think I'm going to be in this small triangle region right there. And so I have to figure out what these 3 intersection points are. Right. So the way that I figure that out is I need to see where certain lines are intersecting one another. I'm going to call these points 1, I'll call this point 2, and I'll call this point 3, so we can kind of analyze them separately. At point 1 is the intersection of which lines? It's 1/2 x equals y and x plus y equals 50. So I'm going to do a substitution here. I'm going to write x plus 1/2 x equals 50. I just took this equation and substituted it into the other one. And so then I have 3/2 x is equal to 50, or x is equal to 100 over 3. And then I have to go back and figure out what y is, plugging it back into this equation here. And so I'll end up with y equals 50 over 3. Because if I have 150 divided by 3, that would be 50. So that's, this is the coordinates of that first point, right? This is point 1. All right, let's do that again for the other points. Point 2 is the intersection of, let's see, well, it's the line y equals 12, and then also the orange x plus y equals 50. So x plus y equals 50. And y equals 12. So this one's a little bit easier to figure out because we know what y is. So point number 2 is going to be 12 for y, and then that would be 38 for x. And then point 3 is the intersection of, let's go back and look at the graph. It's also y equals 12, and then it's also the 1/2 x equals y. Of y equals 12 and 1/2 x equals y. Or x equals 2y, right? So y is going to be 12 and x is going to be 24. All right, so now that we've got our 3 points, we can plug them into our cost function. We had 100 over 3, 50 over 3. We have 38, 12, and we have 24, 12. And our cost function was 53,000x, that was the teacher's salary, and then 23,600y, that was the teacher aide salary. So plugging all these into the calculator, we get, for the first one, 2,160,000. For the second one, 2,297,200. And for the third, 1,555,200. So it looks like the last option is going to minimize costs. So the minimum sorry. Hold on a second. Sorry, I don't know what happened. I just lost all my screens. Okay, so the minimum cost is $1,555,200, and it's when 24 teachers are hired. And 12 teachers' aides are hired. All right, thanks for watching, and send me an email if you have any questions. Have a great day.